Hello everyone, my name is Desheng Zhang. I'm a assistant professor at Computer Science Department, and thanks Rebecca for the invitation. And so today I'm going to talk about the cross-domain cyber physical system for smart cities. Okay? So this is the outline of this talk. First, I'm going to talk about what is the CPS, what is cyber physical system for smart city, and also two research projects to justify my contribution in the detail. Then some ongoing project. And finally, some privacy and security issue about the CPS in the setting of smart cities. Okay, is my voice okay? Everyone hear me okay? Okay, perfect. So what's the CPS? The basic idea we're going to see is the communication, computation, and control integrated not only in our smartphones, laptops, but also in this large-scale physical system. For example, smart grid, medical devices, manufacturing, transportation, telecommunication, smart payment, and urban infrastructure. So those physical systems upload their data to the cyber world, and those data will be processed to get the real-world knowledge, and those knowledge will be used to control and improve those physical systems themselves. So that's CPS. And my research is focused on the CPS in the urban area. So why urban area? Because we are in a rapid process of urbanization, which leads to several challenging issues. For example, the traffic congestion and energy consumption. So last year, White House announced this 160 million smart city initiatives. In the next few years, several government agencies will support a research project for the smart cities. And for my research, we have been focusing on the cross-domain urban system in different cities around the world. For example, in New York City, San Francisco, Washington, D.C., Rome, Beijing, Shanghai, and Shenzhen. In our largest platform in Shenzhen, which is the twin city of Hong Kong with 14 million people there, we have been focused on different kinds of urban infrastructure, including taxi, bus, subway, truck, loop sensor, electric vehicle, smart cars, and cell phones. So those are amazingly complex distributed systems interacting with each other at a real time in urban scale. So to understand those large-scale urban infrastructure, those systems, it's better to study their data. For example, I have been working on several types of data across different urban domains. For the transportation domain, we are working on the vehicular GPS data. And for the telecommunication domain, we're working on the cell phone CDR data and the Wi-Fi data. And for the finance domain, we're working on the smart car transaction data. And for the geography domain, we're working on the road network, including the intersection, road segment, regions, and point of interest. So with those data and the system, the research vision for the CPS is that those urban systems upload cross-domain data to the cloud, and we do the data-driven modeling. And based on those data-driven modeling, we have the cross-domain knowledge to understand the urban physical phenomena. And based on those knowledge, we design knowledge-enabled application to actually improve the urban system by providing positive cross-domain feedback to those systems. Okay, so this is a cross-domain data-driven closed-loop cyber-physical system. And the research goal here is try to understand the urban physical phenomenon by data-driven models and manage the urban physical system themselves by knowledge-enabled services. So this slide gives an overview of my research, actually for my PhD from 2012, like from 5 years ago. First of all, on the urban system part, we have been focused on the data collection in terms of how to collect data more efficiently. Okay. And after we gather this cross-domain data, we do the data-driven modeling. We try to understand the different kind of urban physical phenomena, including the human mobility, travel pattern, traffic speed, passenger demand, and transit supply. Based on understanding of those urban physical phenomena, we have this knowledge. Then we design knowledge-enabled applications such as ride sharing, last mile transit, centralized dispatching, distributed navigation, and advertising to actually provide positive feedback to the urban system themselves to close this control loop. Okay, so the core here, the intellectual core here, we call the cross-domain philosophy. We try to understand the urban physical phenomenon and then improve upon the urban phenomenon themselves. So in this project, I will use two research projects. In this talk, I will use two research projects, human mobility modeling and mobility-driven ride sharing, to show my contribution in a little bit of detail. So the first project is data-driven mobility modeling. So the goal of this project is to model the human mobility at the urban scale in real time. For example, in New York City, how many people travel from the downtown Manhattan to Central Park in next hour? And this kind of mobility has many real-world applications, such as urban planning, transportation, social network, and location-based services. So for the state of art, right now, the researchers try to model the human mobility with different kind of urban system data, including the subway data, bus data, cell phone data, and taxi cab data. But essentially, all those data are small data. They are small sample collected offline and from the single domains, and which lead to biased sampling and overfitting of those models. And in contrast, we try to use this cross-domain opportunity. We have been working on the data from across different urban domains. For example, for the transportation domain, we're working on the CDR data, which is called detailed records. And every record gives us a SIM card ID, a time, a cell tower, an activity. Is a phone call, is a text message, or is a data connection. And for the geography domain, we are working on, for example, intersection, road segment, urban regions, and the point of interest. By combining those two domain data together, we have this cell phone tower heat map. For example, different icon here indicate different cell towers, which is in the Chinese city Shenzhen, and the lighter the color and the higher density associated with different towers here. And based on analysis of the trajectory of one cell phone users, we can have origin and the destination for the cell phone users. And we also focus on the transportation data. And for example, we are working on the text data. Our record gives us a vehicle ID, a time, a location, and a status, with the passenger or without the passenger. Based on that, we can infer the origin and the destination for the taxi cab passenger. And we also work on the finance data, which is the smart car transaction data. So every car transaction record gives us a smart car ID, a time, a location, and an activity. Get into the subway station, get out of the subway station, get on the bus, get out of the bus. Okay. Based on the station map, we can have the origin and the destination of the subway passenger and the bus passengers here. So the key, based on those data and the system, the key contribution of this work is a technique called multi-view bounding, and we try to infer the human mobility. Okay, how many people travel from one region to another region in real time, and we consider transportation domain as a view, which can give us some aspect about the human mobility. We can combine the data from taxi, bus, subway to model the human mobility. But we're missing one large piece, which is the private cars. Okay. Currently, there is no urban infrastructure can capture the private vehicle at the urban scale in real time. Okay. Alternatively, we can use the cell phone telecommunication domain as a view to model the human mobility. However, when the user do not use their cell phone, we cannot capture their location with the CDR data. So we're also missing one part of the cell phone user who do not use their cell phone very often. Okay. So here, each view itself is incomplete, but they are complementary to each other. Okay. So the technique we have been proposed is called the data-driven model integration technique, which is called the multi-view bounding. We consider different urban domains at the different views, and we'll try to quantify the bias of individual views, and to bound the range of this unknown phenomenon, which is the human mobility we try to understand, and by this interdependent views here. So essentially, this technique is for a model driven by the data from urban scale collected online across different urban domains. So which fit the classic definition of a big data with a high volume, high velocity, and high variety here. Okay. So since our model is focused on the cross-domain aspect, so our key contribution here is on the variety part. So I'm not going to get into the detail of our cross-domain this multi-view bounding technique, but the key idea here is that we try to bound the range of this unknown physical phenomenon, which is the human mobility, how many people travel from one region to another region by multiple views with a quantified bias. Okay. So we implement our model at Chinese city Shenzhen, so which is the twin city of Hong Kong, and based on our urban region partition, which is given by the Shenzhen government themselves, and different color here indicate a different urban density, and based on this partition, we have this give visualization of our mobility model. Every vertex here indicate the urban region, okay, and One edge linked two vertices together indicate the mobility volume between two regions, and different colors indicate the different urban districts here. Okay, as shown by the yellow vertices, we have lots of mobility around the downtown area. This is for one specific hour from 5 p.m. to 6 p.m. And we compare our model with a classic physical model called the radiation model. Radiation model assumes the mobility is proportional to the population between two regions and disproportional to the distance between those two regions. Okay, and we outperform that theoretical model by 57% in terms of accuracy. We also implement our model at the street level. Okay, for this highly populated downtown area. Okay, this gives a visualization of the incoming and outgoing trips in terms of mobility at the road segment level here. Okay, the lighter area indicates more people coming in or coming out from those road segments. This is every 15 minutes. Okay. So for the evaluation for some quantitative result, we compare our model MPAT with a cell phone data-driven model called WIR. And this gives the result. The x-axis is 24-hour day. The y-axis is a metric called MAPE, and which essentially is the error percentage of errors. And for the early morning and the late night, we found that both models had a pretty high error because of some irregular mobility here. But during the rush hour, the morning rush hour and the evening rush hour, the performance become better because of the commuting pattern. And during the daytime, the error become higher again due to the random mobility during the daytime. But our MPAT, which is the name of our system, is better than WIR, okay? Because we use the cross-domain data set instead of only cell phone data. And to increase our research impact, we convince our collaborator to release some sample data here on our website. If you're interested, we have, for example, the cell phone CDR, truck, GPS, subway data, and also taxi and bus. Okay. So for the big picture here, we try to understand the real-time urban phenomena. And in this project, we use 5 different urban systems across different domains with a new technique called the multi-view bounding, and to model one specific urban phenomenon we call the human mobility. And we generalize this idea to use a more urban system to understand the more urban phenomena. Okay. And based on this understanding, we formulate some nonlinear optimization problem based on a metric to obtain this cross-domain knowledge to design the different kind of novel services in terms of application. For example, ride sharing, last mile transit, dispatching, navigation, and advertisement. So in next project, I'm going to briefly talk about the mobility-driven ride sharing. Okay. So finally, those systems, for example, ride sharing, going to provide positive feedback to the system themselves, improve, for example, the efficiency of the taxi cab system to close the loop here. Okay, so after the data-driven mobility modeling, I'm going to talk about the mobility-driven ride sharing. So one interesting, based on our cross-domain data-driven modeling, is that we can find some interdependent urban phenomena. For example, we use a ratio rho, which is, for example, mobility demand over transit supply to draw this heat map. Okay, this is a city of Shenzhen, different regions here. The lighter the color, the higher the passenger demand, the lower the transit supply, which indicates some imbalance between the demand and the supply, which motivated us to design some ride-sharing service to address this issue. Okay. So, based on our data, we analyzed some ridership issue at a different city. For example, in New York City, on average, there's only 1.3 passenger per trip, which indicates if we use a sedan, there's going to be 70% of the capacity will be wasted. And also, we find similar travel patterns. Okay, a lot of people travel from a similar origin to the similar destination during a similar time. For example, this is a visualization of 500 taxi trip in Shenzhen from 6 in the morning. The red dots indicate the occupied taxi here. We can find a lot in the morning, a lot of taxi from the downtown to the airport. And after they arrive at the airport, they become unoccupied, they directly go back to the downtown area because there's no people to pick up in the morning for the airport, okay? So we found a lot of similar trip here from the similar destination to similar origin. from the similar origin to similar destination. And so a simple solution is to share the capacity here. And when we try to design the servers, there are two kind of related work. T-share, which is the KDD community, data mining community, and also Uber Pool also rolled out at 2014, I think. And but still, they still use the single domain knowledge, mostly from based on the data from their own system, and they did not consider all our urban mobility information. And in contrast, we try to use this new opportunity we call the cross-domain knowledge, and we design different kind of model to capture physical phenomena related to the ride sharing here. For example, we design a model based on the mobility demand, based on the data from the finance domain, telecommunication, transportation, and the transit supply, based on the data from transportation domain and the geography domain, and the traffic speed model and the fare model. And then we combine those 4 different models together to have a comprehensive service we call the co-ride, which is a ride sharing service to minimize the ride sharing cost. And this service also has an impact on different urban domains. It reduces the mileage to deliver all the passengers to their final destination, and also it reduces the energy consumption, and also reduces the fare for each individual passengers, because they split their fares with their co-riders. Okay. And so the key contribution of this project, the co-ride here, this co-ride is a cross-domain knowledge-enabled resource sharing framework. And we have some bounded online approximation algorithm. We have real-world implementation, multi-scale, multi-set evaluation, and some potential opportunity for commercialization here. Okay. So I'm not going to get into the detail of this, for example, 2 approximation algorithm here. But the key idea here is that the mileage obtained by our online approximation algorithm at most 2 times of the optimal mileage obtained by linear programming here. Given the origin and destination for different passengers, we try to do some arrangement about how to couple different passengers together. And our algorithm based on online approximation, and it at most 2 times of the optimal mileage. Because the optimal mileage is too slow to work in real time, so we have to use an approximation algorithm to get the result in real time here. And we have very comprehensive evaluation here, and we test the factor of different, we test the impact of different factor on the performance of our system. The first factor is the scale. We have a regional scale, urban scale, and the national scale. It's 6 million square kilometer, okay, which is pretty big. And we also test the impact of different logistics to the performance of our system. We have the taxi, we have the private vehicle, we have the logistic trucks, okay. Also the impact of different locations. We have the city in North America, we have city in Europe, we have city in Asia, okay. I'm going to start with the impact different scale here. So the first scale is the regional scale. We have a field study in Shenzhen. We rent 3 vehicles, 12 passengers. We do 31 days of the field study, and every passenger is willing to tolerate 5 minutes of delay. Okay. So we pick one region in Shenzhen, and which is close to a subway station. We have a vehicle here. There's some picture about our field study. And we use a simple metric to show the performance of our ride sharing, which is the percentage of reduced mileage because of ride sharing. Since we combine 2 passengers, if those 2 passengers have the same origin and the same destination, if we combine them together, the total mileage will be the half. Okay, that's how we reduce the mileage here. And so this is the result. I have 31 days. I already have a bar here. And the y-axis indicates the percentage reduced the mileage. So on average, we can reduce the mileage by 49%, almost cut in half here. Okay. And since every vehicle can at most host 4 passengers here, and that's why we can almost cut the mileage in half. Okay. So the second scale is the urban scale. We have this data-driven simulation to show the performance if all the passengers in the city is willing to participate in this ride sharing and wait for other passengers to do the ride sharing. We have 14,000 taxis, 6 months of data. So let's give a visualization of the ride sharing traces in terms of a pickup location and the drop-off location. This is the downtown for the Shenzhen. And let's give the result. The x-axis is tolerant delay time in terms of seconds. The y-axis is the percentage reduced mileage. So the key message here is that if every passenger is willing to wait for 300 seconds, which is 5 minutes, we can reduce the mileage by 41% across the city. Okay. So after we do this urban scale evaluation, we were thinking, is it possible we can do an even larger scale, okay? And this is the China Expressway map, and it's like our interstate system in US, and it links major cities in China, for example, Beijing, Shanghai, and Shenzhen. And for this highly populated area, we have this vehicular truck network with 50,000 vehicles, and we do a ride sharing with their traces. Actually, it's not a ride sharing, it's more like a cargo sharing because they share the cargo together. And this gives a one-day visualization of their ride-sharing traces, and we can see there are several big urban clusters from Beijing, Shanghai to Shenzhen. Okay. Let's give the result. The x-axis is still the tolerant delay, but right now it's in terms of the hours instead of seconds. Because in those long distance travel, the tolerant delay should be longer than within one city. So here, the key message is that if every driver or company can tolerate a 24-hour delay, we can reduce the mileage by 19%. So which is a huge number because more than half the cost of those logistic trucks is in terms of the energy, the gas. Okay. So we also use another national scale vehicular network to test the ride-sharing performance at a national scale. We have this 300,000 private vehicle and use their real-time GPS data to test if all the passengers are willing, actually both the driver and the passenger are willing to participate in the ride-sharing and wait for at most 5 minutes, how much mileage we can reduce here. And this gives the one-day visualization of their ride-sharing traces. It's interesting to see the difference between the commercial vehicle and the private vehicle. For the commercial vehicle, their travel distance is kind of long, and most focus on these highways. But for the private vehicle, their travel distance is kind of short, and most focus on the cities with big clusters here. In terms of numbers, for the commercial vehicle, we can reduce the mileage by 19%, and for the private vehicle, we can reduce the mileage by 29%. Okay. So this is the first factor scale. We have the regional scale, urban scale, and the national scale. The second factor we try to evaluate is different logistics. For the same city, Beijing, we have 3 kinds of vehicular network: private vehicle, trucks, and taxis. Let's give the one-day visualization traces of those 3 vehicular systems. And we can see for the private vehicle, since we only sample about 5,000 for private vehicle here, they most focus on here, this area, okay? And for the truck, they most focus on the ring route, the highway, because they are not allowed to get into some certain area here. And for the taxi, they just go to anywhere. In terms of numbers, for the private vehicle, we can reduce the mileage by 24%. And for the truck, we can reduce the mileage by 31%. And for the taxi, we can reduce the mileage by 37%. Okay? This is for the same city, we have different vehicular network here. And our last factor we try to evaluate is the different locations. So we have a project called the Tale of the 6 Cities. We use the text cab system in those 6 cities around the world to test the same ride-sharing framework and to see the performance in terms of the different locations here. With more than 40,000 for the vehicle getting involved, 3 TB of data, okay? And the first city, of course, is New York City. And we can see, let's give the one-day visualization of their ride-sharing traces. We can see there's 2 airports are pretty popular. I didn't show New York here because it's a part of New Jersey instead of New York City. So LaGuardia and the JFK, and there's a bunch of ride-sharing opportunity at the Manhattan area, okay? And in terms of numbers, we can reduce the mileage by 43%. We have a visualization for this. Let me see. So we have a one-day visualization for this taxi ride-sharing in New York City with 30,000 vehicles here, okay? On the left, we have this ground truth, okay? On the right, we have the carpooling situation. A blue point indicates a drop-off location. for example, in the morning, like 7 a.m., we have the cluster drop off in the Midtown Manhattan area, okay? And the pickup location across the different regions in the city. On the top, we have two curves here, indicate the cumulative mileage for two different situations here, okay? For the ground truth, we have the pink curve, and for the ride-sharing carpooling situation, we have this green curve here. As shown by those two curves in real time, we can see our ride-sharing can always reduce the mileage, accumulated mileage, by about 30% to 40%, okay? So the second city is San Francisco. We can see there's a bunch of ride-sharing opportunity at the downtown San Francisco, to SFO, and some people also go to OAK, which is the airport in Oakland. And in terms of numbers, we can reduce the mileage by 19%. And the next city is Rome, and we can see there's a bunch of, there are many opportunities for ride sharing at the Vatican City, and also go to FCO, which is their capital airport. And we can reduce the mileage by 21% if our passenger is willing to participate and waiting for at most 5 minutes. So next city is Beijing. We can see the opportunity pretty good for around the Tiananmen Square here. And we can reduce the mileage by 37%. And the next city is Shanghai. And we can see from the Oriental Pearl Tower, we can have a lot of ride sharing opportunity here. Okay. And we can reduce the mileage by 31%. The last city is Shenzhen. In Shenzhen, we have three kinds of taxis. We have urban taxi, suburban taxi, and electric taxi. For the different color indicate their ride-sharing choices, we can see for the urban taxi, they can go all over the city, but they are more expensive. Okay. For the suburban taxi, they cannot get into the downtown of the city. They are cheaper. Okay. They are mostly focused on the suburban area. And for the electric taxi, theoretically, they can go all over the city, but they have to be close to their charging station because based on the current technology they are using, they have to be charged for at most 6 hours without the single charge. Okay, with the single charge, they can operate at most 6 hours. Okay, it even worse during the night and summer because you have to turn on your air conditioner and turn on your highlight. That's why they consume more energy. Okay, so most they will focus on their charging station here, like shown by the blue points here. Okay, a summary for the evaluation. We test the performance of the impact of three kind of factors to the performance of our system. The first one is the scale. In terms of the scale, it seems that the larger the scale, the lower the benefit because we have some geo constraint here, okay, for the ride sharing. And the second factor is the logistics. It seems that the commercial vehicle has a better performance than the private vehicle. But since we only had a limited data for the private vehicle, it's hard for us to make any conclusion now. But we believe this is a very good direction. And for different locations, it seems that we found the three key factors: terrain feature, population, and number of vehicles in the taxi cab system, which will decide the performance here, right? And for the most existing work, they will focus on one specific scale, one specific type of vehicle, and one specific city. And our work advanced the state of art by three directions, and in terms of different scale, different logistics, and different locations here. Okay. So we have some real-world impact, and after we publish our work, we received an email from a startup company in London. Actually, they do this food delivery. Okay, it's called Deliveroo, which is very popular in I think in UK. And they have an app here. Okay, you can order the food you like through the app, and then they will buy They will tell you how long your food is away from you. They will buy the food for you, and they will deliver it to your workplace or home. This is around 2015, so Uber Eats is not there yet. Okay, and we see this problem as ride sharing problem actually for the food takeout. They have the similar destination, similar origin, similar destination, shared route, and some timely delivery requirement. But there are some new challenges, okay? For example, the worker and they enter and live in the system in real time because mostly they are part-time worker here, and different from the taxi driver, they are more like the full-time job. And also, since this is in London, there's a lot of different real-world factors. For example, the traffic, the weather, and the capacity, which is the size of the box you carried. Okay. Right now, because the traffic is so bad, they cannot use the vehicles. They have to use they cannot use cars. They have to use the scooter and the bikes. and the timing issue, of course, and the food type, which is pretty interesting because you don't want to mess up with the smell of the Chinese food, with the Indian food, with American food. Okay, they have different compartments inside their container, and also the uncertain origin. For example, if I want a Big Mac, okay, they can get this burger for me from different McDonald's, okay, because they taste the same basically. And but which location they will go is based on the real-time location for the worker, okay, and also the real-time request for the people nearby me. So it's a kind of very interesting challenge here. And the big picture behind this project is to improve urban efficiency by sharing economy. And we used to share a book and a DVD, maybe we still do. And right now I have a lot of new services like Uber, Car2Go, Zipcar, and Airbnb. And so the key contribution, our key contribution here is that we design a resource sharing optimization framework. We use the cross-domain knowledge from to design different kind of data-driven models. And we have some groundwork for very comprehensive evaluation and the potential commercialization here, okay? So after those two projects, I will talk about some ongoing project here, okay? And the first ongoing project is to model a human population, okay, and with the multiple cell phone network. All the existing work, there are several kind of, very interesting direction based on the cell phone data to model the different urban phenomena. Human mobility is one of them, but all the existing work, they use the data from single carriers, okay, AT&T or Sprint or China Mobile, something like that. And but since the user uses different kind of, it's very common for one city to have different carriers. So if we only use the data from a single carrier, can introduce some bias and lead to overfitting of the model. So in our work, we try to combine the data from different cell phone network here and to do some partition and do some estimation in terms of population and density, and then we design some service. And these two figures give visualization of a real-time population based on two cell phone networks. Okay, every cell here, let's see, can we see it? Yes, every cell here in the different color indicate different population. For the first network, we have about almost 4 million users. We have 3.5 thousand and towers. This one will have 2.5 million users and 3,000 towers here. Okay, if we combine those two cell phone network together with some technique for the partition, we have more fine-grained spatial partition because our cell becomes smaller based on the intersection of the two different cells here. And we compare the result of our multi-cell data-driven model with ground truth, which is obtained by the remote sensing together with the census data, okay, to give us some pretty good estimation about very fine-grained, very fine-grained regions, 100 meters times 100 meters, okay? But it seems that this data is static, okay? Just 1 year per picture, okay? So, but based on our model and with the real-time cell phone data, we can have this human population and density model for every hour, okay? This can enable a lot of novel application here. So the second project is this state-level mobility prediction. This is China, okay? And we have a province called Guangdong, which is the most wealthy province. It's like California here, okay? And the size of Guangdong is similar to the size of Florida, I would say. The weather is also the same, okay? We have 300 million people there. And this is their ETC system, okay? Electric toll collection system. It's like our EZ Pass here. Every point here indicate different toll station. And we have highways here, okay? They are pretty expensive. If you travel, it's better to take the train or something like that. And for example, inside the city, we also have different toll stations. This Shenzhen. Shenzhen is like an economic hub of the entire China, and they also have different stations inside the Shenzhen. And based on the ETC data, we can actually model the state-level mobility at the station level. For example, every point here indicates the station. We have this radiation kind of mobility pattern here, and here every point indicates ETC station, which is pretty big here. We see two hubs. One is Shenzhen, the other two clusters. One is Shenzhen, the other is Guangzhou, and combine this stationary we call this a sensing system because it can give us the origin destination for individual vehicles. Combine this stationary sensing system with a vehicular network at the state level, for example, private vehicle and logistic trucks. We can use this mobile sensing together with the stationary sensing to model the mobility, real-time mobility at the state level. I think the most work model the human mobility or vehicular mobility is within the city instead of at the state level. Okay, and so this several projects about the research in my group, but since this is a workshop about privacy and security, even though I'm not working on those two directions, I'm still going to talk about briefly, okay, just two slides. The first one is that in our community, for the data-driven modeling and the service, mobile sensing, it's very important to have real-world data, but it's hard to get. But several pieces of work has been proposed to how to release the data under the different privacy. Okay, release the data from in Montreal about their subway and train data and bus data, and also in US there's some work about release the cell phone data, AT&T and Sprint, and also in New York City the taxi cab data. But all those different papers, they are focused on the single domain data release under different privacy in different cities. Okay, what if we want to release the data across different domains in the same city? So I think let's have some new challenges on the opportunity for the people here to working on how to release the data, cross-domain data in the same city under different privacy here. Okay, and the second topic is the security here. And in this talk, I talk about this data-driven service for the ride sharing by combining different kind of data-driven model driven by the data from different cross-domain urban system. And but similar to other service, this kind of service is vulnerable to DOS attack. For example, if we have some people to generate some fake request, and the dispatcher will dispatch the vehicle to different locations, then they cancel the request. We have to do the redispatching, okay? Then they generate more fake requests. Then we have to do the dispatch again, okay? In this case, we try to, there's no way we can efficiently manage those mobility service, okay? And one possible direction for this is to design different kind of fare models to increase the cancellation fees. In this case, we can somehow to address this issue. But this is just one perspective. And the conclusion, okay? In this talk, I'll talk about the cross-domain cyber-physical system for smart cities. We try to design and deploy knowledge-enabled application based on the data-driven model from cross-domain system. And based on the data from the urban systems, we have a lot of imperfect cross-domain data in terms of they are very sparse, they are implicit, they are untimely, okay? Based on those data, if we want to do some modeling here, and the result here is more like heterogeneous in terms of the different scale, different timelessness, and the different granularity, okay? We need some work to address this heterogeneous model here. And even though we have this perfect knowledge to design the service, we still need some domain expert to improve our user experience in different service. And then we need a platform to collect the feedback of our service. In that case, we can improve upon, okay? Even though with those three directions, I see the privacy and the security is in the core of this loop here. And even though I'm not working on that, I'm willing to collaborate with the people who are interested in this direction to study the privacy and the security issue in the setting of the smart cities. Okay, so let's conclude my talk. Thank you very much. Any questions? Yes.
I'll go later. I have a multi-part question.
How much benefit is there to adding one domain to another?
That's in terms of different things you try to model. If we model the human mobility, we can see we compare our model with a model driven by, our model is a cross-domain model driven by the different data across the different urban domains. We compare our model with a model driven by the cell phone data alone, which is we call it weird. So that's for different, it's kind of interesting because for different location, different time of day, the benefit is different. And during the rush hour, we basically have the similar performance. But for the non-rush hour at some rural area, our performance is much better than the single domain data-driven model. It's like a spatial temporal dependent. Yeah.
Right, so I remember that. Where's the ground truth in that graph?
Yes, interesting. The ground truth is that we use because this is mobility, we cannot use the census data to get the ground truth, but we use the cell phone data connection. It's like the fingerprint for the cell phone user to infer their mobility. And those data are collected by periodically handshake with the cell phone, between the cell phone and the tower. Based on that, we have a complete trace for the single cell phone users. Based on that, we get the ground truth. But those data we do not use that data in the design. We only use the regular CDR in the design because those data are collected to test the peak performance of their infrastructure. So it's kind of useless for the carrier to collect those kind of tower level handshake data. But for the CDR data, it's mandatory for the building purpose, of course. That's why I think most of the work right now are driven by the cell phone CDR data instead of tower handshake data. But we use that data to get the ground truth to do the comparison here.
Okay, multi-part. Doesn't have to do with the privacy, it's all about smart cities.
Okay.
There's a different type of ride-sharing program in Washington.
Yeah.
It's in Northern Virginia. To get into Washington from Northern Virginia, you often have to take what's called high occupancy vehicle roads, where you have to have so many people in a row, and in a car.
Carpooling, right?
Sorry?
Carpooling, right?
Well, it's a little bit different. So there are people who actually, it's called slug lines. That people go to park and ride areas far away from the city. And then one person driving will pick up other people so that they can go on those faster, cheaper roads. So it would be like Uber or Lyft, but in this case, it's for free. And that takes more cars off the road. So that's just a different type of ride sharing. Also, you mentioned Uber Lyft hauls Lyft line, which does the same thing where you share things. Also, you didn't talk about autonomous driving cars, and that would be a really good way to apply this to make it even less expensive. So I guess now I get to the question. You mentioned that there's wasted space and capacity.
Yes.
So when are you assuming that in a taxi or with a sedan, you have one person in the front seat and 3 people in the back seat?
Yes, this is a strong assumption. That's why in the evaluation I say, if every passenger is waiting to participate, our performance is more like the upper bound. If every passenger is waiting to participate, how much mileage we can reduce. If they don't want to participate, they just do the single taxi. We cannot do worse than that. We can only improve the performance if they are willing to participate.
Right, and I think the challenge you have is the assumption that someone who's taking a taxi would be willing to share a taxi with 3 people going to slightly different destinations instead of having express service to them. So if there's a way to model preference, then I think that would make a stronger.
It's a very complicated issue because there's a lot of real-world human factor inside. Because we are kind of a computer scientist, we deal with the system and the data. So yes, exactly.
With people who deal with human factors.
Yes.
Because then you'll have a better model for which you can make projections.
Yes, exactly.
Thank you. Excellent talk.
Thank you.
So I was going to ask that same last question, but also there must be differences when we're looking at human ride sharing versus cargo sharing. I imagine the incentives are much larger for cargo sharing. So have you actually worked to understand the nature of cargo, mom and pop versus large companies and their willingness to share? Is there a lot of reasons for it?
Yes, the data we got from this cargo. Let me see. This cargo data we got from a logistic company. They manage about 20 small companies here, and they're headquartered in Shenzhen. And right now we know their real-time cargo information. We know their real-time location. We kind of know their origin and the destination. But sometimes they take a different route because of the real-time traffic issue on the national highway. It's pretty complicated. But right now the reason they collect the data is for the real-time monitoring. They try to see where my truck is, instead of calling for the driver. And here our big assumption is that because we assume that the delay time is going to be longer than within the city, and if for example, every driver or every company is willing to wait for 24 hours a day, what is the benefit we can have? But I understand that, for example, for some cargo, for some stuff, package, they're very time sensitive. We cannot, wait for 24 hours to do it, especially for some seafood or something like that. But this is one way we can think about it. Okay. Yeah, so this is one factor we should consider in the future to make it more practical. Yes.
And I would suspect that that's probably an easier place to start with the real world.
Real world, exactly. Yeah.
Isn't there also there's a privacy issue also with sharing, right?
Yes,
yes. Maybe I'm willing to go in a taxi, but I don't want this guy to know where I'm going.
Yes,
so, the same with the cargo, presumably.
Right now, the Uber Pool doing that, but it's hard to do because you have to be another passenger has to be on board to deliver the first passenger first. So it's harder to avoid that issue unless you don't go your final destination. You go to the one at the intersection. You just walk up for the final maybe 100 meters, something like that. Yeah.
Yeah. So for the London food takeaway project,
Yes.
the driver is like employee or is just a sharing, like a P2P nature?
There's two kind of people working on that, and one is like they are pretty regular, but they only working in the peak hour. For example, the lunch, which is their most popular time frame of the day. And also there's some people that get in. For example, they do it 1 day a week, something like that. There's some random worker, but those workers not very popular because they need some training to do this, and you cannot. I didn't mention that because I don't know how to work on that, but I believe this. I believe this cross-domain knowledge and the data-driven model can benefit the autonomous driving as well. Yeah.
I see there's application. They're similar.
Okay.
But you have a lot of data that's very interesting. And what they do is they simply use a bidding process.
Okay.
And any drivers, regular something, when they register, they authenticate, they do some bidding. By pay $10, you're willing to deliver not just the food, anything else.
And then package.
And they packaging and come through. So this is real P2P, and sort of like
crowd delivery. Yeah.
Yes. So now you add one more dimension, is like bidding part.
Yeah.
How much money you're willing to pay, and then how much. Because of that, then people maybe say, I'm ready to do it. So, yeah.
Yes.
Very interesting. Yeah.
Thank you. Yes.
I also have a couple of questions. First, my third question is about the source of the data. So you have so many data there from car rides, from phone data. So how do you get this data in what form? I mean, do you get real microdata because there are obviously huge privacy issues here?
I work with one research institute in China, and they have a collaboration. They mostly like the National Research Institute / startup there, and we don't have the raw data here. And every summer, I go there at least 2 months, at most 4 months there to work with them. And sometimes they give us some highly aggregated results, like the model, the density at the urban region level. That's why we can write a paper and work with them together. But all the raw data are securely in their server. So it's like we tell them what to do, and they process data for us, and we write a paper together. We do the project, but we don't touch the raw data they have there. Yeah.
Yeah, research data sets.
So my second question is about modeling, about the gravity model that you mentioned. You said that it works quite well with your data, because, in some of the first publications, they said that it did not work well in small scales. It was more like to describe commuter data, over much longer flights, 30 or 50 miles and above. And speaking of commuters, do you take this into account when you model New York City? Because definitely there is a huge influx of commuters from New Jersey. So in principle, in your model, you will have many sources in New York City, but with no destination, basically.
Yes.
Right?
Very good question. For the first project, cross-domain data-driven human mobility modeling, we only implement our model in Shenzhen. That's why we have those different data sources. We do the modeling. And for the New York one, we only do the ride sharing. For the ride sharing, we know the origin and the destination, then we can do this. We did not implement our model, the human mobility model in New York City. Because we can try, but we don't have this fine-grained cross-domain data to implement our model. We only do it in Shenzhen. But for the ride sharing, we do it in New York City. Because if we know the origin, destination, the capacity, the passenger, the time, we can do the ride sharing there. Okay.
Perfect. All right, let's get to our break if there are more questions.